Welcome to the deep dive. Today, we're jumping into something that's, well, pretty much everywhere. Large language models. You interact with them constantly, maybe without even realizing it. The AI helping write code, generating text, even assisting in complex medical stuff. They're incredibly powerful. Their influence is just massive and growing. But here's the big question, the mystery we're digging into. Despite all that, there's still mostly black boxes, right? How do they actually make decisions? What's really going on inside?
That's exactly the challenge. And it hits on a really core assumption in AI interpretability work. This idea that each little piece inside an LLM, say a single neuron, only represents one single simple concept. We call it monosemanticity, like one neuron, one meaning, simple.
Okay, but what's the latest research finding? Is that simple picture holding up?
Yeah.
Or is it more complicated?
Yeah, that's where things get really interesting. The surprising thing, and what the research we're looking at today really highlights, is that there's more and more evidence showing these internal bits are, well, not simple at all. They're often polysemantic, which means one component encodes multiple, often totally distinct concepts, sometimes all at the same time.
Wow, okay. So the black box just got blacker, or at least more complex. If one part does many things, how does PRISM help us figure that out? What's its approach?
Right, so PRISM, that stands for Polysemantic Feature Identification and Scoring Method PRISM, is this new framework that tackles that assumption head-on. Its whole goal is to give us richer multi-concept descriptions for these features, not just one label. It's about getting a more nuanced view, which is pretty essential if we actually want to understand how these things work. Think less single tag, more detailed profile.
Okay, let's unpack that. So interpretability research, the basic aim is to figure out what each bit does, right? Give a human-readable job description to a neuron or maybe an attention head, those parts that weigh how important words are in a sentence.
Exactly, assigning functional roles.
But if they're polysemantic, like you said, doesn't that throw a wrench in the works? How can you assign one role if it's doing 5 different things?
Precisely. That's the crux of it. Polysemanticity means one feature, maybe a neuron, is tuned to multiple different ideas or patterns, and these ideas can be semantically really distinct, not just variations on a theme. You can even think about it like from an efficiency perspective. It's how the network crams so much function into its parts, like one pipe carrying completely different signals.
And that's the issue with older methods then. They usually just spit out one description per feature. And the source material says this can obscure the true complexity, like trying to describe a complex tool by just one function. It reminds me of trying to explain a smartphone by just saying it makes calls, you miss 90% of what it does. It limits how well we can grasp what's really happening inside. And that's why PRISM sounds like such a step up.
Exactly. PRISM is designed specifically to capture this inherent complexity. It doesn't force a single label. Instead, it generates multiple descriptions for a single feature, acknowledging its diverse roles.
And the research gives a really great example, doesn't it? Feature 3815, layer 47, GPT-2 XL, an MLP neuron, which is like a core processing unit. Okay, so previously other methods might have said, maybe this is monosemantic, one main job.
Right. Possibly just one thing.
But PRISM comes along and says, hold on. It actually lights up for a wildly diverse set of things, like quantities, numbers, time periods. Okay, that makes sense, but also for personal experiences or opinions. Totally different. And then this one's really specific. Indefinite articles before contextual nouns, like a or an. So numbers, feelings, and grammar rules, all in one neuron. That's kind of mind-bending.
It really is. And just to be clear, when PRISM talks about a concept, it means a cluster of input-specific words or tokens that trigger similar activation patterns in that neuron. So one neuron can be linked to several of these concept clusters, reflecting all the different kinds of input it responds strongly to.
So PRISM isn't just finding these multi-concept features, it's doing more, right? What are its main contributions?
Yeah, there are 3 key things. First, the framework itself, generating these more precise multi-concept descriptions. That's the core innovation. Second, it provides quantitative ways to evaluate these descriptions so we can actually measure how good they are and compare different methods. And third, it delivers the first real analysis, showing just how diverse and heterogeneous these individual feeders and LLMs actually are. It puts numbers on the complexity.
This sounds really involved. Can you walk us through how PRISM actually does this, that 3-step process?
Sure, it's quite methodical. Step 1 is percentile sampling. So PRISM takes a big chunk of text, runs it through the LLM. For the feature we're interested in, say that neuron 3815, It finds all the sentences that make that neuron fire really strongly. We're talking top percentile activation levels. And it samples carefully across that top range to get about 1,000 examples that really show what makes that feature tick, what it responds most strongly to.
Okay, so you get the greatest hits for that neuron. What happens next?
Step 2, concept clustering. These high activation sentences get turned into numerical representations, or embeddings. They use a sentence encoder for that. Then they apply k-means clustering. It's a standard technique to group similar items. Here, it groups sentences that activate the neuron in similar ways. They typically use a fixed number, like 5 clusters. This tries to find recurring themes or patterns in why the neuron fired so strongly.
5 clusters, okay. Trying to balance detail with something humans can grasp.
Exactly. Then step 3, cluster labeling. This is where it gets clever. For each cluster, they take the top activating sentences, maybe 20 or so, and feed them to another very powerful LLM. In this case, they use Gemini 1.5 Pro.
Using an AI to label the AI.
Right. And they prompt this powerful LLM to generate short, natural language summaries, descriptive labels for each cluster. They even highlight the specific words, the tokens, that had the peak activations within those sentences to kind of guide the labeling LLM.
And the researchers specifically mention that you need these really high-performing LLMs, like Gemini Pro, for PRISM to work well, to get labels that are actually faithful and meaningful.
Yeah, it shows how complex the task is. It takes a sophisticated AI to make sense of another sophisticated AI's internal state.
Okay, so you've got these multi-concept descriptions generated by an AI, but how do we know they're any good? How do we know they're accurate or useful? Talk about the evaluation.
Right, crucial step. They have 2 main scoring approaches. First is description scoring, which they call CoSy. It measures the quality of each individual description. It uses 2 metrics. One is AUC, area under the curve. Basically, how well does the description separate text examples that match the concept from random text examples?
Higher AUC means a clearer, more precise description.
Exactly. It shows the feature really responds specifically to that concept described. The other metric is MAD, mean activation difference. This just measures how much stronger the feature activates for the concept-specific text compared to random text. A bigger difference means a stronger signal.
Okay, quality scoring. What about measuring the polysemanticness?
That's the second part, polysemanticity scoring. This quantifies how different the multiple descriptions for a single feature are from each other. They calculate the similarity between all pairs of descriptions generated for that one feature. If the descriptions are very different, low average similarity, the feature is considered highly polysemantic. If they're all very similar, high similarity is more monosemantic.
Makes sense. And they did some sanity checks too, didn't they, to make sure this wasn't just finding random patterns?
They did. Really important checks. In one, they took valid descriptions and just randomly assigned them to other features, completely mismatched.
Okay.
In another, instead of sampling high activation sentences, they just fed the system completely random sentences.
And the result?
Big drops in the scores. Both AUC and MAD plummeted compared to using PRISM properly, which is great evidence. It supports the idea that PRISM's descriptions are actually faithful. They genuinely reflect what the feature is doing, not just noise.
Good. So then they benchmarked it, PRISM versus other methods like GPT-explain, output-centric, across different models, GPT-2XL, Llama 3, Gemascope. How did PRISM fare?
It did very well. The main takeaway was that PRISM, especially what they call the max variant, which just takes the score for the best of its multiple descriptions, it generally achieved the highest AUC and MAD scores across almost all combinations of models and feature types they tested.
Almost all.
Yeah, for instance, with GPT-2XL, PRISM hit an AUC of 0.85, MAD of 2.98, clearly beating GPT-explain. There was one slight exception. Output-centric did a bit better on Gemascope SAE features.
Ah, SAE features, those sparse autoencoder things.
Exactly. They're a different way of trying to find meaningful features inside models, so it suggests maybe different interpretation methods work better for different types of features. That's an ongoing debate. Also, an interesting side note, neuron-based features generally seemed easier to get reliable interpretations for compared to those SAE features.
That is interesting. And what about where these features are located? Did they find differences between, say, the early, middle, or late layers of the models?
Yes, they did see some patterns. The middle layers often seemed easier to interpret. The AUC scores peaked there.
Suggesting maybe that's where more concrete concepts form.
Possibly. But polysemanticity itself didn't show a clear trend across layers. It really varied a lot depending on the specific model and the type of feature. For example, those Gemascope SAE features. They showed the highest levels of monosemanticity, suggesting they might be isolating more singular functions.
Okay, so PRISM works. It generates better descriptions, it quantifies complexity. But what does this tell us about the LLMs themselves? How does it help us actually understand what's inside?
Well, it lets researchers map out the concept space within a model. They can take all the descriptions PRISM generates for many features, cluster those descriptions together, and then generate meta labels, summaries of the summaries, essentially. This creates these higher-level, human-understandable categories of what the model seems to be representing internally, like building a conceptual atlas of the AI.
Can you give some examples? What kind of categories did they find in, say, GPT-2 XL?
Sure. They found clear semantic categories, things like positive experiences or events and activities, basic meaning. They also found domain-specific clusters, like digital tools and resources or legal and administrative affairs, shows specialized knowledge areas.
Okay.
But it wasn't just meaning. There was syntactic diversity, too.
Hmm.
Features related to time date information or structured data, focusing more on grammar and language structure,
Right.
and fascinatingly, combined representations, like a concept labeled product information that seemed to blend syntactic ideas of quantity with the semantic context of food or recipe.
Wow, syntax and semantics mixing within concepts.
Exactly. And another really cool one from GPT-2 small SAE features was listeria contamination.
Listeria, like the bacteria.
Yeah. It suggests concepts that link meaning with pragmatics, the real-world context and intent, like recognizing not just words about contamination, but the implied warning or public safety message.
That's a deep, understanding the implication, not just the words. It makes you wonder, could this lead to a kind of shared vocabulary? A way to talk about what any AI model is representing, regardless of its architecture?
That's definitely a hope, yeah. A more standardized way to compare internal representations.
All right, the ultimate test then, the interpretability showdown. AI versus human. How well did PRISM's AI-generated labels match up with what a human expert thought?
Where they did this direct comparison. A co-author, who didn't know what PRISM had generated, looked at the same sentence clusters and the highlighted words, and came up with their own labels, and also rated how polysemantic they thought each feature was.
Okay, example 1. A known polysemantic neuron from GPT-2 XL. Layer 10, feature 603. What happened?
Both PRISM and the human agreed. Definitely polysemantic. Lots going on.
Agreement on complexity. What about the specifics?
There were differences in the labels. The human might say separation or encryption, while the LLM generated things like recollection or personal experiences.
Different angles.
Yeah, but interestingly, they did agree on some more specific, less common topics that popped up, like special occasions and even U.S. presidents. So some overlap on the finer points, too.
Okay, now the other side. A monosemantic neuron. GPT-2 XL, layer 40, feature 60667. How did that compare?
Much higher consistency here.
Yeah.
Both PRISM and the human came up with very similar descriptions. The core idea was clear to both. It was about units of time or time measurements, strong agreement when the function was simpler.
So what does that comparison tell us overall about how AI describes versus how humans describe?
It seems the LLM, Gemini Pro in this case, tends to be a bit more verbose. It often contextualizes the concepts more, gives you the surrounding flavor. The human annotator tended to be more direct, maybe more abstract or essentialized.
Like the AI gives you the scene, the human gives you the theme.
Something like that. But here's the really crucial part. The scores for polysemanticity. The human's rating versus PRISM's calculated score showed a high correlation.
So even if the exact words differed, the overall judgment of complexity lined up well.
Exactly. It suggests PRISM's automated scoring is capturing something real about the feature's complexity that aligns with human intuition. That's a big validation.
Okay, let's pull back. What's the big takeaway from all this, the core value of PRISM?
I think it's really that PRISM is the first system to automatically find and quantify these multiple activation patterns for a single feature. It gives you both the descriptions and scores for quality and polysemanticity. It's a much more nuanced toolkit.
And why does that matter? Why do we need this nuanced toolkit?
Because understanding these internal mechanics is absolutely crucial if we want to build AI we can trust. Think about debugging. If an AI makes a mistake, especially in a high-stakes area like medicine or autonomous driving, we need to know why. Was it misinterpreting data? Did one feature activate incorrectly because it was juggling too many concepts? This multi-concept view helps us move towards that systematic understanding. It helps interpret not just single components, but potentially complex interactions between them.
And for you, the listener, getting your head around this kind of deep dive into AI's inner workings, it's really important. It's about understanding the path towards making these incredibly powerful tools more transparent, more reliable, and ultimately more trustworthy. It's about ensuring we can actually understand and fix them when things go wrong.
Now, it's not perfect, of course. There are limitations. PRISM currently focuses on descriptions in natural language. So really complex mathematical or algorithmic patterns the model might learn. Those might be hard to capture in just words. It might miss things that aren't easily verbalized.
Right. And using those super powerful LLMs like Gemini Pro to do the labeling, that's computationally expensive right now, isn't it?
It is. That's a practical constraint. Scaling this up requires significant resources.
But looking ahead, what's next? Where does this research go?
Well, you could imagine exploring hierarchies of concepts. Do lower-level concepts combine to form higher-level ones? Developing even better ways to evaluate these descriptions, perhaps involving more rigorous human testing or community benchmarks, would also be valuable. It's definitely an active area.
So a final thought to leave everyone with. If our most advanced AIs, when we kick inside, show us that even their individual components have these complex, multi-layered, polysemantic ways of operating, what does that suggest about the nature of understanding itself, both for machines and maybe even for us? Something to think about.